Hey everyone, I'm Beau from the Decisions to Actionable Knowledge Group, DTAC. I'm here to introduce Poisson process radial basis function networks, or PoRB-Nets, which are Bayesian radial basis function networks that behave a bit more like GPs than Bayesian neural networks. So I'll start with some motivation. Bayesian neural networks capture function space uncertainty by placing priors on the weights of a neural network. Unfortunately, common weight priors are able to encode little functional knowledge. On the other hand, Gaussian processes place priors directly in function space and can easily encode function space properties via the covariance function. For example, the RBF covariance function encodes two properties: the amplitude variance, which controls the vertical scaling of the functions, and the lengthscale, which controls the smoothness of the functions. Our question is, can we encode these properties in a neural network? Compared to other approaches that use optimization, we'll attempt to directly encode these properties in the prior. To get these properties, we use radial basis function networks, which have been around for a while and have received some recent attention. Unlike feed-forward networks, RBFNs have scale and center parameters and use a localized activation function. The diagram here shows radial basis functions, which are Gaussians in this case, with the C parameters as the means and the S squared parameters as the precisions. The network output is the linear combination of these basis functions weighted by the W's. So our goal here is to design a prior that decouples amplitude variance and length scale. So consider a radial basis function network that's fairly smooth. It's shown as the blue line. The red lines are the individual radial basis functions that make up the network. If we add more radial basis functions, the network will be less smooth. But in addition, the network will have a higher amplitude variance as the basis functions start to add up. To counteract the basis functions adding up, we can simply make them narrower. Notice the RBFN now wiggles more without being stretched out vertically. And this is unique to the prior we use. So mathematically, we say that the number of hidden units, i.e. the width of the network, is Poisson distributed with parameter lambda times the volume C of the domain of the center parameters. In other words, the integral of lambda over C. Additionally, we set the scale parameter of the basis functions to be lambda, thereby scaling the basis functions based on their concentration. With this prior, a higher lambda value implies a larger number of basis functions that are each narrower. Here's the full prior. The combination of a Poisson prior on the number of hidden units and a uniform prior on the location of the hidden units, i.e. the center parameters, is equivalent to what's called a homogeneous Poisson process. We put normal priors on the output weights and bias as in a standard BNN. Note that the number of hidden units is inferred from the data. Later, we'll discuss an inhomogeneous Poisson process, but for now, let's see what we can do with a homogeneous Poisson process. With this prior, we can derive the covariance function, which we show in the paper is nearly constant over the input space. Here, we just illustrate this concept with functions sampled from the prior shown in red. The black dotted lines are the amplitude variances from these function samples. For comparison to PoRB-Net, we have a GP with an RBF kernel and a BNN with a Gaussian activation function. Notice the variance of PoRB-Net and the GP is nearly constant over the input space, while the variance of the BNN concentrates near the origin. The BNN also has a smaller length scale near the origin. How the variance and length scale of the BNN change over the input space will depend on the activation function, but it won't be stationary. For PoRB-Net, we can easily make the amplitude variance larger by increasing the hidden to output weights variance, or make the length scale smaller by increasing the lambda parameter, allowing us to control the prior as we would with a GP. And I think this is a really important point. When you use a GP, whether you use a stationary kernel is a key choice that you have to make. But when you use a BNN with a standard prior, you're implicitly choosing a non-stationary prior whether you like it or not. If you want stationarity, we show that with a simple prior over an RBFN, you can get it. And this can have really important consequences for posteriors. So here's the posterior predictives conditioned on data from a function that's the same everywhere, f of x equals 0. Consistent with the priors we saw before, the BNN has relatively more uncertainty near the origin as compared to away from it, whereas PoRB-Net has even uncertainty over the input space. Looking at the BNN, is this the posterior you want? Maybe, but certainly maybe not. But if you use a standard BNN prior, this is what you're getting in some form. And notice we're using HMC in this case, so this is not an inference issue. So far, we've considered a constant intensity, lambda. If prior information is available, this can be replaced with an intensity function, lambda of C. Now the scale and concentration of the basis functions both vary over the input space. In the plot, we use a stepwise intensity function, resulting in a smaller length scale above 0. The upcrossings of 0, i.e. the number of times the samples cross the line y equals 0, is a way of measuring the length scale. But what if we want to infer an intensity function? Well, we can simply change from modeling the intensity as a homogeneous Poisson process to an inhomogeneous Poisson process. This is just a point process where the expected number of points in a region T is the integral of the intensity over T. For inference, we use a sigmoidal Gaussian Cox process, which models the intensity as a GP squashed through a sigmoid, so it's always positive. Before getting to some results, here's an existing model we use for comparison. It's a GP that uses a non-stationary kernel that looks a lot like an RBF kernel, except with a length scale function L of x that varies over the input space. By further modeling the log of the length scale function with another GP, the length scale function can be inferred. So now we'll do inference on synthetic data drawn from that same GP from the previous slide. In this example, the ground truth length scale function is a sine wave. We plot the inverse of the ground truth length scale as this orange dotted line here. And we see that the inferred intensity of PoRB-Net, shown in purple, matches the pattern in the ground truth. The inverse of the length scale function inferred by the LGP also picks up in the patterns in the ground truth. So here's a few more synthetic data sets, each with different ground truth length scales. In the second and third columns, the inverse length scale decreases from left to right. The only difference is the second column has a gap in the data. And in the last column, the ground truth length scale is constant. Notice that PoRB-Net and the LGP infer qualitatively similar length scales in all cases. Now we have some empirical results. Note that the goal here is really to illustrate properties. These data sets are all very small, so we can do full HMC inference. And on all models here, except the regular GP, do use HMC. The data set in the top is one of the synthetic ones I already showed. You can see that PoRB-Net and the LGP learn that the function that varies a lot on the left, while the BNN gives lower uncertainty there. Overall, I think the LGP looks qualitatively the best in this data set. The data set in the bottom is a time series of heart rate data. You can see that PoRB-Net and the LGP learn to smooth out the posteriors on the right, where the data is quite smooth, where the BNN doesn't quite do this, while also giving much higher uncertainty near the origin, which is consistent with the priors that we saw before. The table shows the test log likelihoods for all data sets. PoRB-Net, when we confer the intensity, the second column does pretty well. As a sanity check, a GP with an RBF kernel does best on the only stationary data set. So here's a few concluding thoughts. We showed that PoRB-Nets can separately encode stationary amplitude variance and length scale and infer the input dependence of the length scale if that's desired. We focus on theoretical properties in this paper. For future work, we're interested in how you could scale this model, how it could be applied to deep RBFNs, and we think it could be really useful for Bayesian optimization. So thanks for listening.